It is my great pleasure to welcome you all to the inaugural lecture of Professor Ferenc Krausz, a Nobel Laureate in Physics 2023. Professor Krausz has recently joined our Department of Physics at the University of Hong Kong. A luminary in ultra-fast laser science and quantum optics. Professor Krausz's arrival will bring a new dimensions to HKU's research excellence. His joining will further solidify our global leadership in upstream research and open new frontiers that transform both science and society. As you all know that, science thrives where curiosity, talent, and opportunity converge. Today's gathering is more than a celebration of extraordinary research achievements. It is a statement of HKU's vision to be a place for the world's greatest minds. It is a testimony that our interdisciplinary collaboration can drive far-reaching global impact and sustaining support from the Hong Kong SAR government. Professor Krausz's work stands at the frontier of human capability. It explores timescales so short that they allowed us to see the very motion of electrons. You know that, we have a block of metal, and inside there's molecules or electrons floating inside, but very tiny, moves extremely short. And his technology and discovery really enables us to make a measurement or capture a movie of that every movement of the electrons inside of particles or proteins or solids. This is a science that fundamentally changed our view of nature. This is the spirit of discovery we wish to nurture here at HKU. By welcoming Professor Krausz into our academic community, we not only strengthen HKU's role as a world-leading university transforming humanity's future through fundamental research. We'll also reinforce Hong Kong's growing stature as a global hub for scientific excellence. As a beacon of the world-class talent, HKU is committed to fostering an environment where curiosity, collaboration, and innovation meet. We aim to shape a better future for the humanity and the world. This commitment is especially vital in an era of unprecedented change. Universities are engines of both knowledge creation and societal impact. We will engage the world best, empower students to think boldly, and ensure that positive impact born here in Hong Kong ripples far beyond. As we look forward to today's lecture, I invite you to see it not just a scientific research, but a new way of seeing how fundamental science advances the life of humankind and its civilization. One that benefits not only our city, but the world. Ladies and gentlemen, please join me in extending a heartfelt welcome to Professor Ferenc Krausz as he begins his journey at HKU. Thank you.
Thank you, President, for the insight. So now please allow me to take a moment to introduce Professor Krausz's remarkable academic journey. Professor Krausz was born in Hungary, where he studied theoretical physics and electrical engineering before embarking on a career which would place him among the most influential experimental physicists of our time. Apart from his new role as a chair professor at the Department of Physics at HKU, he also served as a director of the Max Planck Institute of Quantum Optics in Germany and a professor of experimental physics at Ludwig Maximilian University of Munich. Recently, he established the Center for Molecular Fingerprinting in Hungary as its founding director. His journey reflects both deep intellectual curiosity and a relentless drive to expand the limits of what is possible in science. Professor Krausz is a pioneer in the field of attosecond science, a domain that enables us to observe and control the motion of electrons in atoms, molecules, and solids at the timescales of billions of a second. In the early 2000s, his team succeeded in generating and measuring isolated attosecond pulses of light, a breakthrough that opened the door to direct observation of electron dynamics. This has provided scientists with an unprecedented view of fundamental processes, including chemical reactions, charge transport in materials, and the interaction of light with matter. For these contributions, Professor Krausz was awarded the 2023 Nobel Prize in Physics, alongside Pierre Agostini and Anne Louilly for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. Beyond fundamental physics, attosecond technology holds promise for advances in semiconductor engineering, energy materials, and even medical diagnostics, where ultra-fast imaging could reveal biological processes in real time. It is rare to hear directly from a scientist whose work has created an entirely new subfield of physics and opened the possibilities across multiple disciplines. Without further ado, please join me in welcoming Professor Ferenc Krausz to deliver his inaugural lecture, which is titled Towards Affordable Preventive Healthcare, How Basic Science Addresses Grand Challenges. So Professor Ferenc Krausz, please welcome to the stage.
Is it working? Yes. Dear Professor Zhang, dear Secretary Choi, dear Secretary Sun, distinguished guests, colleagues, and friends. Good evening, everyone. Here in this wonderful lecture theater and online. It is a tremendous honor to take up a professorship at one of the best universities of the world. And it is a tremendous honor to speak in front of such a distinguished audience. My cordial thanks go to President Zhang and the leadership of HKU for enabling this to happen. I would also like to extend my gratitude to the administrative staff for their invaluable support and to colleagues from the Faculty of Science and the Faculty of Medicine for their inspiring efforts to join forces for pursuing the... Does it work better? Okay. Does it work better? Yes, definitely. Thank you. So, just once again, I'm very grateful also to colleagues from the Faculty of Science and Medicine for entering into discussions with us to join forces for pursuing the question that I posed in the concluding part of my Nobel lecture. What is the most economically viable set of health data that enable comprehensive and dependable monitoring of human health, and to what extent can controlled light contribute to their acquisition? The quest for the answer constitutes a challenge that no one person, no one laboratory, no one country can possibly master. My being here connects 4 institutions from 3 countries, from 2 continents, and is largely motivated by the hope that together we may have a chance. I encourage everyone who can contribute to join us, either for the pursuit of our grand goals or for saving the dreams of next generation of scientists wherever they are in danger, currently in war-torn Ukraine. Only together we can make a difference. Thank you so much. Oh, I feel definitely better with this. The Max Planck Institute of Quantum Optics, briefly MPQ, and the chair of laser physics of the Ludwig Maximilian University of Munich, briefly LMU, located at the campus Garching near Munich in the south of Germany, accommodate our research group that has been called briefly Otto World, using controlled fields of laser light for triggering, controlling, and probing electronic dynamics in atoms, molecules, liquids, and solids in order to gain ever deeper insight into fundamental electron phenomena on the genuine attosecond time scale. In 2015, we started wondering whether these advances may possibly benefit our ability to protect human health. To address what I believe is among the greatest challenges humankind faces in the 21st century, which is displayed on this chart, reflecting the correlation between the average number of healthy life years and the GDP per capita in a selected set of countries of our planet. As you see here, in developing countries, newborns have a perspective for a healthy lifespan some 10 to 15 years shorter than their counterparts in developed countries, on the top of which, by the way, you see Hong Kong. So you have chosen a very nice place to live because you have the highest chance to live healthy here in Hong Kong. Almost half of the Earth population has to accept, nevertheless, this gloomy prospect to be prepared for a much shorter, healthy lifespan. And I guess quite understandably, more and more are reluctant to do so, and we all know the consequences. Before we can tackle a problem, we need to understand its root. In this particular case, there are certainly several. In what follows, I'd like to focus on what I believe is one of the main ones. Every year, 17 million people under the age of 70 die of, and many more lose their ability to work due to so-called non-communicable diseases, briefly NCDs, with the four most prevalent ones being cancer, diabetes, cardiovascular, and chronic respiratory diseases. 86% of them in low and middle income countries. The tremendous loss of life and life quality and the loss of immense resources. In Germany, more than 45,000 Hong Kong dollars per capita per year, implied by late diagnosis of chronic conditions, can only be mitigated by preventive care that is able to catch the most prevalent killers in their early stage when treatment is much less expensive and has a much higher success rate. Equally importantly, this care must also be affordable. It must be affordable to be implemented on a population scale. An enormous challenge. And we believe that most probably only blood-based diagnostics offers a ray of hope. Thanks to a key hallmark of being alive, homeostasis, a process that keeps our organism within the range of favorable or ideal internal conditions. As a result, the molecular constituents of human blood are regulated within narrow person-specific concentration ranges to maintain proper functioning of the organism. Many of the millions of different types of molecules may be up or down regulated by chronic conditions, substantiating our hypothesis that human blood is likely to carry the molecular information needed for comprehensive screening for NCDs, and prompting the question whether at least for a physicist, whether cost-effective physical technologies can possibly access molecular signals from human blood that are sensitive and specific enough to NCDs for capturing and diagnosing them at an early stage to allow timely interventions. A bit more careful considerations make us realize that the question is not quite complete. If I have to be honest to you, actually, it's plain wrong. The success of any measurement, and hence the detection of a disease, which must always be based on some sort of measurement in modern medicine, the success of any measurement depends on the signal to noise ratio. Reducing the noise is equally important or equally useful than as increasing the signal. And the noise, in our case, when we do a medical measurement, is of biological origin. Its dominant part is of biological origin, which is affected by the, as you will see in a moment, by the healthcare modality used. Therefore, the right question reads as follows: can physical technologies and a suitable healthcare modality access NCD-induced molecular signals, disease-induced molecular signals that exceed biological noise in their pre-symptomatic stage and enable comprehensive screening for NCDs on the population scale? This is the question. This is the question that our team seeks the answer for at Garching by München, at Garching near Munich in Germany. here, including also our designer, Dennis, who contributed the graphics and animations to my presentation, our team in Budapest and Szeged in Hungary, and meanwhile here in Hong Kong, with the support of President Zhang, Vice President Gong, Professor Tse, Mr. Yao, Dr. Wong, and Professor Ip, to name only the most important colleagues supporting our endeavor, with some of them even substantially contributing. Last but not least, I wish to extend my cordial thanks to Yan So and Cindy Chan and the media team for allowing this event to happen. Thank you. The question guiding our research centers on physical technologies and healthcare modalities, both of which must be advanced, perhaps even quite dramatically, for precision individual-based preventive care. Indeed, contemporary laboratory medicine captures molecular levels mostly one by one via single analyte assays, which is not really scalable, not at all scalable to hundreds or thousands of molecular parameters, and compares the measured values with population-based reference ranges, which suffers from large interpersonal variations among healthy individuals. This is the biological noise I referred to before. Future preventive healthcare calls for a revolution in both respects, and that's what we mean to initiate in the framework of our Protecting Health initiative, a multilateral intercontinental cooperation. Single analyte assays of contemporary laboratory medicine will be complemented or possibly even largely replaced by state-of-the-art molecular profiling of cell-free human blood by means of mass spectrometry, nuclear magnetic resonance spectroscopy, and infrared electric field resolved molecular fingerprinting, which together offer the capability of gaining unprecedented amount of molecular information from human blood. These three platform technologies together offer the chance to collect 4, 5, or maybe 5,000+ parameters out of human blood. You should compare this with the several dozens that contemporary laboratory medicine can afford on a routine basis. Precision prevention relies on person-specific reference ranges. You will understand in a moment why is it so important, which can only be acquired by repeated measurements within a short period of time and frequent recalls to capture unfolding conditions, unfolding diseases at their earliest stage. Implementing this Protecting Health study concept with its repeated baseline, within just a few months, several blood donations, and high-frequency follow-up over the years afterwards to a large cohort is second to none all over the world and opens the prospect for establishing personalized preventive care based on pre-symptomatic early predictors. Consider a molecular variable, be it a spectroscopic feature affected by a group of molecules or the concentration level of a particular analyte that is highly stable over time. So if we measure it repeatedly, we get almost the same value. The value is basically depicted here along the y-axis, basically. So you see it fluctuates just very little, and we can determine from this little fluctuation the mean value and the person-specific reference range. This generally is much narrower than the spread of the same variable in a healthy population, because even healthy people are just so different. We are all different, not only in terms of our fingerprint, we are also different in terms of the molecular makeup of our blood. And that's why the population-based reference range which contemporary laboratory medicine is using is generally much broader than your own person-specific reference range. If this, just imagine that this parameter is now sensitive to a particular condition. So you start developing a disease and this very parameter responds. Either it starts increasing or it starts decreasing. Now we just assume that this response is an upregulation, so it starts increasing. So what happens then? That's what actually happens. The onset and development of this condition in this example will cause an upregulation as depicted here by the red dots. If this occurs before symptoms manifest, we have discovered a pre-symptomatic biomarker. Its monitoring would then be likely to reveal the disease much earlier, namely right upon acquisition of the first red values, than symptom-guided contemporary healthcare could diagnose it. Because contemporary healthcare is just, in most cases, waiting until you develop symptoms, which drives you to a doctor, and the doctor will, after some examination, come up with the clinical diagnosis that may happen much, much later. But how to actually discover the best pre-symptomatic biomarkers, which could be so useful and so important for early disease detection and screening? Disease-induced changes are often buried under the broad population distribution of any blood parameter. One of them is shown here. Repeated measurements provide access to the narrower within-person distributions, allowing to sort those individuals, the values of which are distributed around the same mean value. The values of these individuals are depicted by the gray distributions. Knowing these person-specific distributions now allows to narrow the baseline, the healthy baseline, by shifting all these gray distributions to the center of the population curve. By shifting each of these groups that much that the mean value kind of becomes equal to the population mean value, in this way we gain what we call an average intrapersonal distribution. This is the gray distribution at the bottom, which is naturally more susceptible to small changes over time because it's much narrower than the population distribution. For instance, this change might occur just due to healthy aging, as sketched here for a hypothetical variable that is supposed to be insensitive, not responding to any NCD, to any chronic disease listed before. And we just assume that the aging is just slightly shifting the value of this parameter, but doesn't cause any other big change. If, however, a disease-sensitive variable is considered, which we assume now in this example, this tends to be, as I just assumed before, upregulated by some of the developing prevalent conditions. And this upregulation leads to an outgrowth of a tail in this distribution upon subsequent visits. The area of this outgrowth is supposed to increase upon subsequent visits due to the progression of the disease and increasing number of new onsets. It is very important to note at this point that observing these tails as a hallmark, actually, of a prevalent NCD in this distribution, that observing these tails as a signature of disease-induced upregulation of the selected parameter does not rely on the knowledge of diagnosed cases at this point. Even in their absence, epidemiologic data inform us on the incidences of NCDs, and hence we know that the growing tail indicates the response of the parameter to the risk or onset of one or more of the most prevalent NCDs, which will dominate basically any change in this direction. Hence, long before all new onsets are diagnosed, towards the end of the 10-year study period, we shall be able to identify the most promising spectroscopic, proteomic, metabolomic, and lipidomic variables with small within-person variations and strong response to one or more prevalent NCDs as candidates for signaling the risk for or onset of these conditions in a cost-effective and highly sensitive fashion. Why cost-effective? Because instead of measuring the thousands of variables that are accessible these days with these platforms, we shall be able to optimize the underlying molecular profiling technologies for those variables that meet these conditions. And this way we can reduce costs, we can increase throughput, we can increase sensitivity. But how did I actually end up working on this? The story started on the turn of the new millennium when our group at the Technical University of Vienna produced the first isolated pulses of attosecond light, the briefest man-made events with which the fastest processes outside the atomic core, the motion of electrons could be captured and reconstructed in slow motion replay, exemplified here by electron migration in organic molecules. Electrons bind atoms together to form molecules, the basic building blocks of life. Their spatial distribution is depicted by the green cloud here, and their motion in the quantum world manifests itself in the deformation of this cloud. These motions are apparently of utmost importance for our life, for our biological and modern life likewise, and probably that's why the Royal Swedish Academy found the ability to capture them worthy of this couple of years later still unbelievable recognition. The attosecond metrology we originally developed for tracking electronic motions has also proven capable of sampling the oscillation of light waves. The solution was looking for a problem and found it some 15 years later by capturing molecular vibrations in human blood in real time. Imagine we expose cell-free blood to an extremely brief infrared laser pulse, which brings the molecules in vibration over a broad range of frequencies covered by the spectrum of the laser pulse. The vibrating molecules in turn emit coherent infrared light in the wake of the excitation. Just as this tuning fork generates acoustic waves, I try to make you hear it. Following its sudden excitation, whilst these sound waves oscillate only a few hundred times per second, which our ears can directly detect, you can just hear it, the infrared molecular signal oscillates several 10 trillion times per second, several 10 trillion times. These hyper-fast oscillations can now be captured by attosecond metrology. We refer to the resultant signal as the infrared electric field molecular fingerprint of the blood sample because it is highly specific to individuals. The method capturing it has been dubbed infrared electric field molecular fingerprinting, briefly infrared fingerprinting, and constitutes the only profiling modality in our phenotyping platform that can detect signals from any types of molecules. The fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition, because different molecules make different contributions to the overall signal. We have meanwhile verified this for a number of chronic conditions, including 4 different types of cancer: lung, prostate, breast, and bladder cancer. These curves show how the true positive rate can be increased at the expense of increasing number of false positives by varying the discrimination threshold in the classifier algorithm. The overall detection efficiency can be best characterized by the area under this curve, which is referred to as the AUC value. As an example, I show here the electric field molecular fingerprints of patients diagnosed with non-small cell lung cancer and well-matched healthy controls, 470 each. The conspicuous differences between the red and blue fingerprint traces allow training an algorithm for the detection of lung cancer. To this end, we use 90% of the measured fingerprints for training the algorithm via machine learning and the remaining 10% for testing it. The diagram on the right-hand side shows the classification efficiencies of the resultant algorithm evaluated for resectable non-metastasized stages of lung cancer with relatively good prognosis. The results are promising, but not yet good enough for clinical use. I'd like to recall that the detection efficiency depends not only on the disease-induced signal, that is, the differences between the red and blue curves, but also on the noise, on the biological noise, that is, on the sharpness of the reference. A reduction of the spread of the blue traces originating from the heterogeneity of a healthy population should boost the classification efficiency just in the same way as the increase of the disease-induced signal would. This spread could indeed be reduced by replacing the references so far taken from a control cohort by ones collected longitudinally from the same individual before he or she contracted the disease. And now we are back at the longitudinal follow-up. We know, meanwhile, that this spread could indeed be largely reduced by replacing these references. And here is the first experimental proof, thanks to the study that is underway in Hungary which is the world's first large-scale repeated baseline high-frequency follow-up study. Meanwhile, with 11,000 participants altogether, we plan to recruit 15,000. Here, thanks to the repeated baseline, we can evaluate the person's specific reference ranges. And this, in the case of infrared fingerprints, we see that this is basically shown by the violet curve for different spectral components of the infrared fingerprint in comparison with the spread of the same components across the entire cohort. The intrapersonal variability is reduced typically by a factor of 2 to 3, which would imply a corresponding reduction of the spread of the blue traces here if these blue traces would be from the same person who eventually contracts this disease. So we could now simulate this by just reducing this spread as if this would be just at the level of the intrapersonal variations. And we can check how much easier the classification algorithm figures out from the red curves that you have contracted lung cancer. And here is the result. So it's the result, the consequence is a dramatically improved classification efficiency of early stage lung cancer just by using the cancer-induced infrared signals that we can measure today. We used the cancer-induced infrared signal we can measure today, and we just assumed that we use as references basically the fingerprints that we have collected from the same person before contracting the disease. This is a first indication of the power of longitudinal follow-up for precision prevention. The capacity of EMF to capture different types of cancer prompted the question whether the method may be capable of doing more than detecting a pre-selected, isolated condition. And first encouragement was provided by a recent study conducted in collaboration with researchers from the Helmholtz Zentrum in Munich, in which 4 common conditions, chronic conditions, could be detected in a single measurement. And perhaps even more remarkably, the absence of all 4 conditions in the healthy subgroup of the cohort could be verified with an AUC of 90%. This study actually highlights the general focus of health monitoring, the reliable exclusion of ever more chronic conditions for early warning preventive care. We don't want to exclude just one condition like current screening programs do, but a broad range of severe chronic conditions. These promising findings prompted us to create the critical mass that may be able to establish the foundations of affordable precision preventive healthcare with a global initiative which we dubbed protecting.health. In Hungary, the prototypical Protecting Health study is underway, as I already mentioned to you. The pilot phase of Protecting Health in Hong Kong is due to start soon in cooperation between the newly founded Institute for Precision Prevention of Hong Kong U and the CTC of Hong Kong U, one of the leading clinical trial centers of the world. The pilot phase can be readily scaled to a 15K study, just as it is being implemented in Hungary once the government funding becomes available to this end. Simultaneously, the federal government of Germany has allocated resources for the Protecting Health Germany study, but the starting date of this node of the network is still open. Once established, our global network of 3 standardized Protecting Health studies will collect almost 1 million blood samples over the next 10 years across diverse ethnicities to provide access to NCDs with lower incidences and allow us to gain evidence of the universality of the integrated molecular phenotyping approach, which, along with accompanying health data, will be transferred to the Protecting Health Center in Budapest, where the samples will be stored in a cryogenic biobank at minus 180 degrees to preserve their quality over decades. At the same place, the samples will be analyzed with the Protecting Health multimodal phenotyping platform in a building which will be completed in about 2.5 years from now, by mid-2028. So once again, this very complex is supposed to accommodate this cryogenic biobank, the database collecting all the health data of the participants, of course, in an anonymized way, and the phenotyping center, which will analyze the data. The blood plasma samples and their accompanying clinical data will all will be contributed by the ProHealth partners for training the proprietary ProHealth screening algorithm, which we dubbed PH 1.0, for early detection of prevalent non-communicable conditions. Naturally, PH 1.0 will be owned jointly by the partners. To summarize, the Protecting Health study design enables the discovery of those blood parameters which, among all currently accessible ones, most reliable inform on the onset of prevalent NCDs in the earliest stages of their development by first selecting those most stable over time, implying the narrowest person-specific reference ranges, then filtering out from this subset those developing the most conspicuous, steadily increasing outgrowth in the visit-by-visit evolution of their average intrapersonal distributions, as discussed before. The profiling modalities are then being optimized for these selected pre-symptomatic NCD predictors for sensitivity and throughput, and hence for minimized cost. All these steps can be accomplished in the absence of clinically diagnosed new onset cases. While those diagnosed cases accumulate over years to eventually allow establishing causal links between outcomes and parameter changes. With these links, the first screening algorithm for prevalent NCDs will be trained for gaining actionable health insights into the major non-communicable conditions, including cancers, cardiovascular, respiratory, metabolic, and hopefully even neurodegenerative disorders at the early stage of their development, based on the correlated and hence highly specific change of hundreds of early predictors. The cause we have set out to pursue is bigger, much bigger than ourselves. It's bigger than any one person, any one laboratory, any one country. It requires the multi-country collaboration that we are building, thanks to the support of President Zhang and the leadership of the university and of the government. With your support and with all the unfolding collaborations, we have a chance to succeed. If we do, the participating countries will establish themselves as the global pioneers of personalized preventive medicine and underlying healthcare technologies, to the benefit of future generations in Hong Kong, Hungary, Germany, and all over the world. Thank you.
Thank you, Professor Krausz. Thank you, Professor Krausz, for this very enlightening and inspiring talk. Now we have time for questions from the audience. If you have questions, please raise your hand, and please kindly keep your question brief because we want to accommodate as many questions as possible. Yes, questions, raise your hand, please. Any questions? Okay.
Professor Krausz, I have a question. 2 key principles on your process of, on this treatment process are longitudinal intraspecific data collection. In developing regions where there may be warfare or unstable conditions, are there certain methods that can be used and be implemented to ensure a proper viability when collecting longitudinal interspecific data for diagnosing NCDs?
I'm not entirely sure I understood your point. So what exactly is the point? Could you repeat the question?
Two key factors in your implementing idea is longitudinal intraspecific data collection. And this involves collecting data over large periods of time, and in certain developing countries, it may not be feasible to collect data over large periods of time?
Yes. Obviously, the clinical studies are not being implemented in developing countries, right? I mean, Hungary, Germany, Hong Kong are developed countries with a highly developed healthcare where we can rely on the implementation of our SOPs, standard operating procedures, very precisely. This is extremely important to gain reliable insights. But once the method is developed, actually. The implementation, I hope, will become much more simple, because basically it's just really a blood draw and then doing the measurement. So you will not need to preserve, for instance, you will not need to set up a cryogenic biobank in the individual countries which would eventually like to use the developed algorithm for screening, because the measurement potentially can be done if the instrument is at least at a central hospital of the country is available. The measurement can be done essentially instantly, and then basically the infrared fingerprint or the proteomic profile or the lipidomic profile that is being obtained is just stored, and the same procedure is repeated a year later and is compared whether there is any change. So the implementation of the study in this phase is of course much more involved, and this is happening in highly developed countries. That's obvious.
There's a question from the last row. Oh, sorry. Sorry. Yeah. So, okay. So, yeah, Professor.
Okay. Thank you very much, Professor Krausz. Very good lecture, and I've learned a lot. Two simple questions, actually. The first one is, how expensive or convenient is this test? Because it requires us to longitudinally collect samples, et cetera, et cetera. I mean, I'm asking about the cost effectiveness of this assay.
Yes, this is, of course, a very important question. The costs probably for this study will still be quite high because the technology is in its infancy and all the instrumentation is quite expensive. I would guess that it's on the order of something like $200, 200 euro. This is the price tag for acquiring all these molecular variables, up to the 3,000, 4,000, 5,000 or more than 5,000 variables. My hope would be that this price tag will be substantially reduced if the biomarkers are found, so we will not be able, we will not have to evaluate 5,000 parameters, but eventually maybe only 300 or 500. This will make the method cheaper, and basically, if there will be a demand for these technologies, then the instrumentation will also become cheaper. So these two factors should result in another factor of 2 or maybe even more of price reduction. So eventually, our strong hope is that the price tag for the entire panel will be below $100.
Thank you. Can I ask a second simple question?
Yes, please.
And that is, I assume that this is like fingerprinting detection of different diseases, etc. And of the various cancers that you've looked at, the fingerprints are very different, am I right?
They are distinctly different. That's true. This is also a very good question. So we can not only distinguish basically one cancer from the healthy fingerprints, but one cancer from another cancer. So obviously the signals are indeed specific to the disease. Thank you.
Okay. So yes, please.
Thank you for a very fascinating presentation, Prof. Krausz. My name is Sam Samarak. I was the Dean of the faculty here of dentistry. So I think the elephant in the room is artificial intelligence, right? To some extent, I just want to seek your view on how quantum computing and all the modern developments we are talking about, how that's going to fit into this program, and that perhaps, I believe, should accelerate the outcomes. Thank you.
Thank you very much. It's a very good point. Artificial intelligence and data science in general is one of the three main building blocks of this entire project. So basically the clinical part is obviously medicine, the measurement part is obviously physics, and there is in between data science, which is being used for actually analyzing the data and eventually teaching the classification algorithm that is supposed to distinguish a person who contracted a disease from a person who didn't. So data science is of central importance here. I would say that currently this is not the main frontier in our very endeavor. I would say we are not limited by the capabilities that the current status of artificial intelligence can offer us. We are more limited by opportunities at the clinical end, at the physical technology end. And these are the frontiers which we are pushing as strongly as possible. Maybe we will eventually advance to a point where actually we will also kind of get closer to the frontiers of artificial intelligence, but we are not there yet. So to what extent this very field is going to benefit from the advancement of artificial intelligence based on quantum computing, that I cannot even guess. But obviously, we need to work on all these frontiers. Honestly, I don't think that if we would stop doing or undertaking efforts in medicine and physics to improve, basically, let me just show this, which is perhaps most relevant for this question. So, in medicine, we are working on making the noise, the spread of the blue curves as small as possible. On the physical side, we try to improve the differences between the red and blue curves. And artificial intelligence helps us to deal with these kind of noisy signals, and to, in spite of all these issues that we have to deal with on the physical and medical side, still distinguish the cancerous signal from the healthy signal here, right? One could now try to guess whether artificial intelligence, if it will be even more advanced, would be able to enhance the ability to distinguish a person with cancer from one without cancer at the current stage of the technology. I would have doubts. I think we need to work on the technology. We need to improve. Basically, we need to maximize the signal induced by the disease, and we need to minimize the noise induced by our heterogeneity, induced by the variation of these signals within a single person over time, as far as possible, and then try to use the most modern version of artificial intelligence to do the best possible job on distinguishing these signals. That's what we should do, I think.
Okay, so I believe there are many questions from the audience, a lot of interest. But for the time's sake, we will have the last question, and please.
My name is Michael Hussein. I'm a thoracic surgeon. That means 80% of my work is lung cancer surgery, so I'm very, very interested in what you're telling us. You've been telling us that the goal is for early detection of asymptomatic disease at a very early stage.
That's right.
I suggest that you can also look at it from a different angle. We spend tremendous amounts of resources monitoring patients with a disease, but we don't know when to take action. So there's tremendous amount of over-investigation, over-diagnosis, and over-treatment. If you can provide a simple, affordable test to tell clinicians when is the sweet spot to perform invasive procedures, when is the best time to perform an operation, that will be a tremendous amount of savings, both on resources and reassurance for the patient.
Thank you very much. The comment is well taken. Unfortunately, this happens to be a great challenge at the moment, because usually upon this kind of follow-up of the patients who obviously have been diagnosed with the disease already, and the question is whether to take real serious action by surgery or not. In this phase, most probably the patients receive already some medication. Unfortunately, the medication does introduce a lot of what we call contamination in our signals because they leave very, very strong signatures. They change basically the molecular composition of our blood. And this is something we would have to struggle and we would have to learn how to deal with. At the moment, we have no solution for that. So therefore, in all our investigations, we actually draw the blood sample from people who are not receiving chemotherapy and these kind of treatments, which would introduce a very, very strong perturbation to the molecular composition of human blood. But maybe sometime in the future, we will be able to deal with this as well by kind of fingerprinting also the therapists to tell the algorithm, hey, this very patient now receives this therapy, and basically filter this part out from the signal and zoom in on the remaining part to try to answer the question that you have posed. Thank you. Thank you very much. Thank you.
So thank you again for this exciting talk. Yes. So with this, we conclude today's lecture. And thank you again for joining us today for this very exciting event. And looking forward to seeing you again for future events.